Suppose we have a function f of x equal x squared minus x plus 2. What happens to this function at values of x near 2? Let's take a look at this numerically. Here we have a table. Let's start at some x value that comes before 2, such as 1.5. We can then investigate the behavior of the function as it gets closer and closer to 2, but not equal to 2. As we get closer to 2, we can see that the values of f of x get closer and closer to 4. Now let's go from the opposite direction. Let's start at 2.5 and go down until we reach 2. According to the data in the table, as we get the x value closer and closer to 2, we get values of f of x closer and closer to 4. We can express this by saying the limit of the function f of x as x approaches 2 is equal to 4. Here is the notation for this. In general, we can use the following notation. The limit of f of x as x approaches a equals L. This means that we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a, but not equal to a. So, as x gets closer and closer to the number a from either side, but not equal to a, f of x will get closer and closer to a number L. Now, let us take a look at a graphical representation of a limit. Here we have the function f of x equals x minus 1 over x squared minus 1. On the right is a graph of the function. Notice that there is a hole in the graph at point 1, 1/2. That is because the function is undefined at x equals 1. This means that as x approaches 1 from both sides, the function approaches 1/2. Even if we had a point at x equals 1, the limit would still be the same, regardless of whether the function is defined at that point or not. This is because the actual value of the function does not determine the limit. Rather, the value that left and right side limits approach gives the limit at that x value. Since the limit from the left side and the limit from the right side of the function are exactly the same, we can say that the limit as x approaches 1 exists and is equal to 0.5. We can notate the left and right side limits using the minus and plus signs as shown. The plus symbol above the number means that we only consider values of x that are greater than 1. This is the same for the minus sign, where we only consider values of x less than 1. Therefore, if the left and right side limits are equal at a point a, then the limit at that point exists, and is equal to that value regardless of whether the function is defined at that point or not. Let's take a look at another example. Here we have the function square root of 2x plus 1 minus 1 over x. The function has a hole at 0, 1 because it is undefined at 0. How do we know that? If we plug in 0 into the function, we get an undefined 0 over 0. However, using a graph, we can investigate the actual behavior of this function. As x approaches 0 from the negative, or left side, the function approaches 1. This is the same for the positive or right side, meaning that both the left and right side limits are equal. Based on the definition of a limit as shown before, the limit of this function as x approaches 0 exists and is equal to 1. Now, here we have a graph of the function g of x. Use it to state the values, if they exist, of the following limits. First, the limit as x approaches 2 from the left. By looking at the graph, we can see that the graph of g of x approaches 3. Now let us find the right-hand limit. From the graph, the values of g of x approach 1 as x approaches 2 from the right. Therefore, the left and right-hand limits are not the same, so the limit at 2 does not exist. Now let's find the limits at 5. As x approaches 5 from the left, the values of g of x approach 2. This is also the same for the right side limit, where the values of g of x from the right side also approach 2. Because these two limits are the same, we have that the limit as x approaches 5 is equal to 2. However, notice that the value of g of 5 is not equal to 2. It is 1. This is because the value of the limit does not account for the actual value of the function at that specific value, but the behavior of the function as it approaches that value. Let's take a look at a new example. Find the limit as x approaches 0 of 1 over x squared if it exists. Let's start by graphing this function. As x becomes close to 0, the denominator x squared also becomes close to 0, meaning that the reciprocal of this will become very large. By looking at the graph, we can see that the values of f of x can be made arbitrarily large, or infinitely large, by taking x close enough to 0. Thus, the values of f of x do not approach a number, so the limit does not exist. In order to indicate this kind of behavior, we use the notation that the limit approaches infinity. This does not mean that we are regarding infinity as a number, but it also does not mean that the limit exists. It simply expresses the particular way in which the limit does not exist. 1 over x squared can be made as large as we like by taking values of x close enough to 0. In general, we can write this expression to indicate that values of f of x increase without bound, or become larger and larger, as x becomes closer to a. We can also do the same thing for negative infinity. The graph of y equals negative 1 over x squared gives a limit of negative infinity at 0, since from both the left and right sides, the graph of the function decreases without bound as x gets sufficiently close to 0, but not equal to 0. Therefore, if the limit at a point is infinite, there is something called a vertical asymptote at that point. The line x equals a is called a vertical asymptote of the curve if the limit at a is either negative or positive infinity from either the left, right, or both sides. Let's take a look at some examples. Let's find the infinite limits of 6 over x minus 5. First, graph the function. Based on the graph, we can see that from the left, the function increases without bound. So the left side limit approaches infinity. From the right, the function decreases without bound. So the right-hand side limit will approach negative infinity. Based on these two limits, we can say that the limit at 5 does not exist, since the left and right limits are different. Thank you for watching this video. Make sure to subscribe and share.